So continuing from where we have stopped, we have said that here when W is equal to X plus Y, that is W is the sum of two independent random variables, then its characteristic function is equal to the multiplication of the characteristic function of the two different random variables. Okay, so when W is equal to X plus Y, then X and Y are independent. At that time, the characteristic function of this W is equal to the multiplication of the two random variables, independent random variables, X and Y. Okay, so continuing from there, let us consider the numerical which we have here, 3.11. So here the characteristic function of the arbitrary single random variable X is from the appendix A is this function. And in the appendix A, we know very well that for the Gaussian random variable, that is what we have as the characteristic function. So this is the Gaussian random variable. We have picked up the what you call characteristic function from the appendix A here. Okay, so in the appendix A, we have mentioned this. Now, if we consider phi x j omega is equal to this quantity, then assuming both x and y are arbitrary Gaussian random variable, then for x it will be this, and for the characteristic equation for the y will be, I need to write here, phi of y j omega exponential of j omega mu y minus omega squared sigma y squared by 2. Okay, so if we try to what you call write for the so to say multiplication of these two, that is sigma the phi x and phi y, the characteristic function of the two x and y functions, then exponential of something multiplied by exponential of some other thing, or exponential of a plus multiplied by exponential of b will give us exponential of a plus b. So that will give us the value which will just turn out to be exponential of j omega mu x plus mu y minus omega squared sigma x squared plus sigma squared y squared by 2. And this, if you see, we can we know very well that if we multiply these two, we are going to get this function. Okay, so in this function we are trying to substitute for phi x and phi y from here using the equation 3.87. 3.87 is used in the equation which corresponds to 3.86. Okay, substituting 3.87 in 86 for the two values, that is phi x j omega and phi y j omega, we are going to get this function, because e to the power of a multiplied by e to the power of b will be equal to e to the power of a plus b. Okay, so once we have that, then we can see clearly that this value mu x plus mu y is equal to mu w, and sigma x squared plus sigma y squared is equal to sigma w squared from the equations which we have already written here as 3.79 and 3.80. So that just gives us that whatever we have is again a what you call phi of j omega, which corresponds to the Gaussian distribution characteristic function for the Gaussian distribution function. Okay, Gaussian characteristic function for the Gaussian distribution function. So equation 3.88 has the same form as 3.87 because this value has to be replaced by mu w, and this value has to be replaced by sigma w squared. Okay, so that establishes that the result of the sum of the two independent Gaussian random variables is also Gaussian. So this is a very important feature that makes Gaussian random variables convenient to use in the engineering practice. Okay, now let us go for the next problem. The next problem indicates here that the if we consider the random variable to be exponential. Okay, and again that is picked up from the appendix A. So for exponential function, the Gaussian random variable will be something like this. Okay, so this is the PDF for the exponential, what you call random variable. Okay, for the exponential random variable, the PDF will be this with the mu x equal to 1 by lambda and the sigma x squared is equal to 1 by lambda squared and the characteristic function lambda by lambda minus j omega. You can write this as lambda into lambda minus j omega inverse, and that is what is mentioned over here. Okay, lambda into lambda minus j omega inverse. Okay, same thing, 1 by lambda squared fxx is equal to lambda e to the power of minus lambda for x greater than 0 and 0 for x less than 0. Now, if we consider W to be a sum of two independent random variables, independent observations of x, which are x1 and x2, then W is equal to x1 plus x2. Then we use the convolution integral for these two. That means the characteristic function for W is equal to the characteristic function of x1 multiplied by the characteristic function of the x2. That also can be considered. Further to that, in addition to the characteristic function, we also said that when we have W as the sum of the two independent random variables, then the PDF of this will be equal to the convolution of the PDF of the two random variables x1, x2. And that's what we are trying to write from here. So that means we will consider FWW is equal to the function which we have written here, minus infinity to infinity, fxx multiplied by fyw minus x dx. And this fxx is nothing but the value, which we have mentioned over here as the lambda e to the power of minus lambda x for x greater than or equal to 0. Also, the fyw minus x, fyw minus x. From here, fyw minus x can be written, and that fyw minus x will be the value which is lambda e to the power of minus lambda w minus x. Lambda e to the power of minus lambda w minus x. And that is what we have here. So this value is f of y w minus x. This value is f of x x. So having written this, lambda into lambda will be lambda squared. That you can take it out. And this, if you try to merge, you will get e to the power of minus lambda w. Okay, because minus lambda x and minus into minus plus lambda x are going to cancel. Okay, so powers will get added up, and once the powers are added up, the minus lambda x and plus lambda x will get cancelled, and we are left with e to the power of minus lambda w. So lambda square into e to the power of minus lambda w, integral 0 to w dx. So if you integrate the dx, you'll get x with limits 0 and w, and that gives us w. So effectively, it will be lambda squared w e to the power of minus lambda w for w greater than 0 and 0 for w less than 0. So that will be the case. Now this, if you see over here, this equation, this is same as the Erlang random variable of order 2. That means when k is equal to 2, order 2 just means k is equal to 2. So this is same thing as the Erlang random variable, PDF of the Erlang random variable for the order 2 or for k equal to 2, and that can be easily seen from the appendix A. Okay, so you can see here, this is the Erlang, what you call a random variable, and this is the PDF of that Erlang random variable for the order k, when k is a positive digit. If k is equal to 2, then this becomes, lambda squared x e to the power of minus lambda x. 2 minus 1 factorial. 2 minus 1 factorial is 1 factorial, and that is equal to 1. So we are left with lambda squared x e to the power of minus lambda x for x greater than or equal to 0. Now this is the same thing as telling, only in place of x we have the variable w over here. We have the variable w over here. So this is also the Erlang random variable, but for the order 2, that is k equal to 2. So if you consider k equal to 2, then again from the appendix A, we can say that mu x will be mu w now. In place of x, we have w. So mu w will be k is to 2 by lambda. Sigma w squared will be k is to 2 by lambda squared. And that is what we have here at this place. Mu w is equal to 2 by lambda. Sigma w squared is equal to 2 by lambda squared. Similarly, you can try to find the characteristic function for the w also. We can find the characteristic function for the w also. So if you want to write, then the characteristic function of w will be the characteristic function of x1 multiplied by the characteristic function of x2. Okay, multiplied by the characteristic function of x2. And the both characteristic functions will be these two values. This, what you call lambda into lambda minus j omega inverse. There's no x term here. Similarly, if you write for y also, lambda into lambda minus j omega minus 1. Okay, so you will get square root of this function because we don't have the y variable at all here. Okay, so the characteristic function for w will be the squared function of this, that is lambda squared into lambda minus j omega squared. Lambda squared divided by lambda minus j omega squared. Okay, so that's the only term which we have, right? So that will be the characteristic function for the same. So this just gives us the what you call PDF for x. This is the PDF for the y, that is w minus x, and the convolution of that will turn out to be this function. Okay, and we have written over here the what you call characteristic function lambda squared into lambda minus j omega to the power of minus 2. So we are discussing here now that the characteristic function of the what you call random variable, which is w equal to x1 plus x2, will be just the multiplication of the two different the characteristic functions, and that will give us lambda squared into lambda minus j omega whole to the power minus 2. Further to that, this figure gives us that this is fxx, right? Exponential, this is the exponential function corresponding to whatever we have written over here, right? And then this is nothing but I can take the what you call mirror image of this, okay? Rotated version of this or mirror image of this, which will come out to be like this, right? From here to here, if I take the mirror image and then you shift it by w, that means it goes forward, which will give me fx of w minus x. So this gives me a shifted version of the rotated form of fxx. Okay, take the mirror image of this, which will become like this, and then shift it by w, we will get this function. Now if you convolve this, then what we are getting here is that we are going to get a Erlang random variable, and the Erlang random variable looks something like this. The convolution of that will look something like this. Okay, the convolution of that is a Erlang random variable which looks something like this. Okay, so this is a Erlang random variable corresponding to whatever equation which we have written over here. Okay, now let us go for the next problem over here. We have considered two zero mean Gaussian random variable, that is mu x and mu y is equal to 0. W is equal to x plus y. Their variances are sigma x squared equal to 3, sigma y squared is equal to 7. Then we will consider here that x and y are independent random variables, right? So under that condition, then we need to find the characteristic function of w. So characteristic function of w is equal to characteristic function of x plus the characteristic function of y. Multiplied by characteristic function of w will be equal to the characteristic function of x multiplied by the characteristic function of w, because we have already derived that relationship. Okay, this relationship we have derived. When w is equal to x plus y, then the characteristic function will get multiplied. Okay, So that just means that when we consider the two, Gaussian random variables x and y, remember that this is Gaussian random variable, and that gives us from the figure the Gaussian random variable function, which is there given over here. Okay, for the Gaussian random variable, the characteristic function is this, and now mu x is equal to 0, and sigma x is given as 3, sigma x squared is given as 3, and sigma y squared is given as 7. So phi of x will be equal to exponential of minus 3 omega squared by 2. Phi of y is equal to exponential of minus omega squared 7, or 7 omega squared by 2. Okay, 3 omega squared by 2 minus 3 omega squared by 2 for phi x, 7 omega squared by 2 for phi y. If you multiply both of them, then because this is exponential, the quantities which are there, 7 plus 3, will get added up, and that will give us the value 10, because again exponential e to the power of a into e to the power of b, e to the power of a into e to the power of b is equal to e to the power of a plus b. Okay, 7 plus 3, that will give us the value 10, and hence we have the expression over here, phi of j omega is equal to exponential of minus 10 into omega squared by 2. So you can write one more step where 2 will cancel with this 10 and we'll get a 5. So this equation gives us that again w is a zero mean Gaussian random variable with a variance which is equal to 10. With a variance which is equal to 10. W is, we don't have mu w, the what we call mean over here. We don't have mean over here. This is similar to, this equation is similar to whatever we have in the appendix over here, except that we have only this term, we don't have this term. We have only omega squared term, we don't have the j omega term there. Hence, the what we call omega w is equal to 0, that gives us 0 mean, and the variance sigma w squared is 10 itself. Sigma w squared is 10 itself. So let us stop at this for today. We will continue in the next class.